Keras is primarily a deep learning tool and therefore supports a vast range of deep learning models. Several applications make use of deep learning models backed by Keras. Let us see how to create one. Deep learning pipelines in Keras can be summarized under following points. The first would be data loading. The data in question is to be loaded into Keras environments using fundamental data loading techniques by using libraries like NumPy. Next will be initializing Keras model. The Keras model needs to be initialized like a variable in basic languages like Java or C. In other words, the sequential modules of Keras needs to be called upon and then the required layers must be added on after another to the initialized model. Compiling the model. Once the model has been initialized and defined, it must be compiled to allow the backend libraries like TensorFlow and Theano to choose the best way to represent the network that has been designed in the model definition. The characteristic step during compilation is to set the optimization algorithm and the metric or set of metrics to evaluate the loss. Compiling the model is like freezing the design pipelines of layers. Next is fitting the model. Due to Keras' extensive simplicity, in order to train a model on the training data, the compiled model just needs to be called upon like any other machine learning models using the fit function. Two important arguments called epochs and batch sizes are passed to the model in this phase so that it can estimate how much data to train upon iteratively. Evaluation of the model. The model can be evaluated by calling upon the evaluate function. This evaluation happens only upon the data points in the training set. So in case the model has overfitted on the training data, it will give very good results, but it will be hard to detect the overfit unless new data is tested upon. Final predictions. Once a satisfactory score is obtained upon evaluation of the model can be moved to the prediction phase. Here, the prediction happens on new data, unlike the evaluation phase where the predictions are internally made on the training data. The predictions are made on new data by calling the predict function on the model and passing the test data as an argument. In the previous slide, we saw how to implement generic deep learning solution through Keras. One of the most popular problems that Keras solves is the image classification. Therefore, in this section, we will go through a more specific implementation of Keras deep learning model. First, data formatting. Image data can come in various shapes, sizes, and color. During the data formatting or processing stage, the data is resized, reshaped, and sometimes discolored or tuned into grayscale images. But this is only done when the color is not a defining factor in determining the classes. Once the images are in the required format, they are loaded as training data. The next step is defining a CNN model. Like we saw in the previous section, model definition had basic and simple model designs. However, CNNs are complex model with multiple layers so that it can adequately distort and play with image features. The primary layers of CNN are convolution layer, which are primarily used for image processing, pooling layer, which is used to reduce image size and map the features to smaller spaces with smart filters, and finally the fully connected layer, which is a neural network where the output for every neuron in the layer is fed to all neurons as input to the next layer. The next is training and evaluation. The model is trained using the fit function and evaluated using the evaluation function. Based on the evaluation score, the model is either sent for improvement or directly sent for generating predictions. Lastly, model improvisation. CNNs can be improved either by increasing the number of dropout layers, which basically introduce slight randomness in the model, by experimenting with the number of convolution layer, by increasing the volume of training data, or by more